before the break we worked out two quantities of interest. We had worked out the probability of exercise of a call option in the Black-Scholes framework. We had also worked out the value of delta as in the Black-Scholes framework. We found that the probability of exercise of call option is equal to phi d 2, whereas the delta value of a call European call in the Black-Scholes framework is phi d 1. Let us continue the exploration and let us now work out the conditional expectation of the stock price subject to of course, the exercise of the call option. What would be the expectation of this stock price given the condition that the call option is exercised? So, that is given by, again we are working in the risk neutral framework. I would like to reiterate, emphasize that we are working in the risk neutral framework. Now, in other words, what quantity we are trying to work out is given here on the first left hand side. E of E means the expectation of ST is the stock price at maturity, subject to the condition that ST is greater than equal to K, because this condition encodes or embeds the chance of exercise of the call option. The call option would only be exercised if ST is greater than K. Therefore, we want to work out or we want to know the expected value of the stock price provided or subject to the condition that the call option is exercised. Let us see where we go. So, this is equal to writing ST as E of log ST. Why we are doing this shall be apparent very soon. We write ST as E of ST, E of log ST, sorry, it's because obviously E of log ST is nothing but ST. So, we have not made any significant detour, any significant digression, simply written ST in terms of the exponential function, and similarly we written K in terms of E of log of K. So, we simply translated them into exponential functions. Now, this is equal to substituting log ST equal to xi, substituting log ST equal to xi for further manipulation, we get this is equal to E of expectation of E of xi is this quantity, log ST is xi. So, E of xi subject to E xi being greater than equal to E of log K. Let us call this integral capital A, where xi is equal to log ST, and xi being log ST is normally distributed. Remember, ST is log normally distributed, log of ST is normally distributed with a mean of this expression and a variance of sigma square t. Let us call this whole expression as lambda, because we will be using it again and again. So, let us abbreviate it as lambda, this mean as lambda, this mean log S0 plus r minus 1 by 2 sigma square whole into t will abbreviate as lambda, right. So, the integral A now becomes 1 upon under, no, please note xi is normally distributed, xi is log ST and therefore, xi is normally distributed. Therefore, when we use the PDF of xi, see when we how will we write the expectation value of this quantity? This is the expectation value, this is my function f x of xi into the probability density function of xi, which is the normal distribution, because xi is equal to log ST, and we have to take expectation between this. So, we shall be taking the lower limit of the integral as log K, upper limit will of course be infinity, because the upper stock price is assumed unbounded, and therefore, the log of the stock price is also unbounded. So, this is what the expression turns out to be when we substitute the value of the PDF of the normal distribution with a mean of lambda and a variance of sigma square t. We have simply substituted this normal distribution PDF here, this whole expression. Then what we have done is we have done algebraic manipulations, nothing else, only algebraic manipulations. What we have tried to do is we have tried to write this expression, the exponent, and this becomes xi minus this whole thing in this form, and then we have tried to complete the square in such a way that we are able to express this, which has you can see this here, it is in the form of x minus mu whole square upon 2 sigma square. That particular form we have tried to capture within the integral, and to do so we in doing so we had this extra quantity, we had this extra piece which was independent of xi and which therefore could be taken out. You can see it is independent of xi and therefore it was taken out of the integral. When you substitute lambda here as the expression, this expression becomes log of h 0 plus r t. This whole thing becomes log of h 0 plus r t, and this remains as it is. Now, suppose I set z equal to this expression, again putting lambda and putting the value of lambda here in this expression, I get z equal to this expression. That simplifies to this expression, and it also gives me d of z is equal to d xi upon, because this whole expression is independent of xi, this when I take the derivative of differential of z, I get differential of xi divided by sigma root t, which is here. So, this is purely algebraic manipulations, nothing more. We substitute z equal to this expression, we have eliminated lambda by going back to the original variable, original value of lambda, and cancellation gives us this expression. And now, the important thing is what will be the limit corresponding to log of k. Let me quickly briefly work it out. Z lower limit ZL, let us call it, is equal to log of k minus log of h 0 minus r minus 1 by I can use this one in fact, minus log of k minus log of h 0 minus r plus 1 by 2 sigma square t divided by sigma root t. When xi takes the value log of k, the value of z will be this, and this is precisely this expression with the minus sign. You can look at this. This expression is nothing but minus t 1. If you put the signs here, this expression turns out to be log of h 0 upon k plus r plus 1 by 2 sigma square upon 2, which is nothing but minus t 1, minus t 1. So, the lower limit is minus t 1. So, minus t 1 to infinity e to the power minus c square upon 2, and this is what we get from this expression. This expression on simplification gives me h 0 e to the power r t, because e to the power log of h 0 is nothing but h 0, e to the power r t I retain as it is. So, this gives me h 0 e to the power r t. So, I have h 0 e to the power r t under root 2 pi into this expression up to minus t 1 to infinity, and this is what is this minus t 1 to infinity, I can write as 1 minus this is as it is, this whole expression 1 upon 2 pi into integral this is equal to 1 minus 1 upon root 2 pi minus infinity to minus t 1, minus infinity to minus t 1. So, that is nothing but, now minus infinity to minus t 1 is for a standard normal variate is nothing but phi of minus t 1. So, this is h 0 e to the power r t into 1 minus phi of minus t 1. Now, as I mentioned earlier, 1 minus n of or phi of x is equal to phi of minus x for a normal distribution, and therefore, 1 minus phi of minus d 1 is nothing but phi of d 1. So, this is the final expression that I get for the conditional expectation of the stock price, given that the call will be exercised, that is subject to the condition that S t is greater than k. So, slightly tedious calculations, but nonetheless very interesting. Right, now we come to the interpretation. We have talked about certain important factors. Let us talk about the interpretation. Now, let us assume that you write a call option, then you have created an obligation to honor the call if it is exercised. However, you see you have written a call, you have therefore taken some risk that if the stock price finishes above the exercise price, you will have to honor the call option, but you can protect yourself. That is the underlying philosophy of this entire Black-Scholes model, that you can create a riskless portfolio. So, you can protect yourself by taking a long position in the underlying stock. You can take a position in the stock, and that's the combination of the short call and the long stock, or delta units of the long of stock taken long will result in a balance, will neutralize the volatility of the call, and as a result of which your portfolio would be riskless. So, therefore, by writing a call and by taking a long position in the stock, you are really exposing yourself to no additional risk. Now, to buy delta units of the stock, if the current stock price is S naught, you will have to make an initial cash flow, a cash outflow at t equal to 0, that is as of today, of delta into S naught, delta into S naught, that is the but delta we have already worked out, delta is equal to phi of d1. So, the cash outflow that as a writer of the call you are required to make in order to retain your risk unchanged, in order to maintain your risk profile unchanged, is S0 phi d1. Against this, what are you likely to receive? You are likely to receive the exercise price if the call holder decides to exercise the call option at the date of maturity of the call. Now, there are two things here. Number one, that you will receive the exercise price only if the call is exercised, and number two, the probability of the call being exercised is given by phi of d2. This is one thing, and the second thing is that the exercise price would be received on maturity of the call, it will not be received earlier. Therefore, what we are concerned with as of today is the present value of that exercise price. So, starting with the present value, if the exercise price is k, its present value as of today becomes k e to the power minus r t, that is today's worth of the exercise price. However, there is a caveat attached to it. The caveat is that this inflow that I will receive will only materialize if the option holder decides to exercise the call. Therefore, it has to be weighed with the corresponding probability, and that is n, that is phi d 2. So, the weighted cash inflow is k e to the power minus r t phi d 2. Hence, the call premium is, as far as I am concerned, as far as the writer of the call option is concerned, which is minus c, is equal to k e to the power minus r t phi d 2, which is my inflow weighted with the probability, minus S0 phi d 1, that is minus c, because I am writing the call. Therefore, c will be equal to S naught phi d 1 minus k e to the power minus r t phi d 2, which is the Black-Scholes equation. Now, interpretation of n d 1 and n d 2, we have already in a sense we have already interpreted them when we worked out the delta and the probability of the call finishing in the money, but let us be more explicit. In the Black-Scholes model, this is my Black-Scholes model. This is the payoff of the call option, and the Black-Scholes model can be written as this expression. If I take E minus R t outside, I can introduce E R t here and this here. Now, the first component of the payoff is minus. Let us assume that there are two components. It can be split into two components. One component is the exercise price, the other component is the stock. The first component is, let us say I buy the call, so I have to pay the exercise price, and therefore, my first component is negative, which is k. It is an outflow for me, the exercise price. Now, the exercise price will be paid only if the call finishes in the money. Therefore, I can write this component as a contingent payoff C1 t, because it is going to occur at t, minus k if S t is greater than k, and 0 if S t is not greater than k, because in this case call will be elapsing, call will not be exercised. Therefore, what is the expected value of this component? It is equal to minus k into p S t k greater than k plus 0 p S t less than k, and this expression we have already found out, this expression is nothing but phi d 2. So, therefore, the expected value of this payoff or this contingent payoff is nothing but minus k phi d 2, but it is occurring at t equal to t, please note this, and it is therefore, the present value of this this component, the expected value of this component is k e to the power minus r t phi d 2. Now, let us look at the stock. The second component that I am going to receive if I have written the call, if I bought the call, the second component that is going to be the receipt of the stock if I decide to exercise the call, Now, when will I decide to exercise the call? When ST is greater than k. So, this is a contingent pay in rather in that I will receive the stock if ST is greater than k, and I will not receive the stock because I will not exercise the call if ST is less than k. The expected value of this expression is E of ST subject to ST is greater than k. Now, please note in this case when we work out this expression, I cannot take ST outside the I cannot simply take ST outside and multiply by the probability of ST being greater than k. Why? Because ST is subject to this ST is dependent on the condition that I have imposed, the constraint that I have imposed. In other words, I have to work out the expectation value of this stock provided that ST is greater than k. In other words, there is a threshold at k, and only if the threshold is touched by the stock price or exceeded by the stock price, then it becomes eligible to contribute to the expectation. If the stock price finishes below that threshold of k, then it does not contribute to my expected value or my expectation of the stock price. I am concerned, I am interested only in the expectation of the stock price provided the threshold is exceeded by the stock price. Therefore, I cannot segregate this as E of as ST into P of ST greater than k, that cannot be done, and this of course is 0. So, this is nothing but this expression is nothing but e to the power r t s 0 phi of t 1. This is what this expression is, we have just worked it out, e to the power r t s 0 phi of d 1. Therefore, its value today, because this is also happening on maturity, this payoff is also happening on maturity. So, its present value will cancel out this e to the power r t factor, and I will have the present value as s 0 phi d 1. So, let us look at the Black-Scholes equation. The Black-Scholes equation then gives me s 0 phi d 1. What is this? This is the present value of the expectation value of the stock subject to exercise of the call minus k e to the power minus r t phi of t 2, which is the present value of the strike price subject to exercise of the call. Therefore, this whole expression is nothing but the present value of the net expected cash flow subject to exercise of the call option, that gives you the current price, which is obviously in tandem with the principles of finance. Now, one small derivation, in fact, it follows from what we have done earlier. Risk neutral derivation of the call price, e to the power of minus r t e q, here q is emphasized because we are talking about risk neutral. This is the payoff. You split the payoff into two parts, S t minus k subject to S t is greater than k, you split it up into E q S t subject to S t greater than k, E q k subject to S t greater than k, put the respective values there, you get the Black-Scholes equation straight away. It is a very small derivation, very attractive, but quite intuitive. Now, some examples. A stock price follows geometric Brownian motion, that is this standard Brownian motion mu s sigma dt plus sigma s dw. A stock price follows geometric Brownian motion with the mu of 16%, this is my mu, and a volatility of 35%. The current stock price S naught is 38. What is the probability that European call on the stock with an exercise price of 40, this is k, and a maturity date, this is t, t is equal to 0.5, will be exercised. It's quite straightforward problem. What is the probability of exercise of the option? We remember it is phi d2. So, we simply have to work out phi d2. And that is one way of doing it. Otherwise, you can work it out from first principles also. You want the probability that the stock price should exceed the exercise price. And in other words, we want that log of ST should exceed log of 40. That is what is important, but we know log of ST is normally distributed with a mean of this and a variance of this expression, and this turns out to be that log of ST. If you simplify this whole expression, you get log of ST is normally distributed with a mean of this and a variance of this, and we want the probability that log of ST should exceed log of 40, that is equal to 1 minus phi. Now, we convert this to a standard log of 40 to this standard normal variate, and we have log of 40 is equal to 3.689. Therefore, this corresponding standard normal variate is 3.6 x minus x bar. This is this expression, the mean upon sigma, which is this expression. So, this is the standard normal variate, and this gives me, this expression gives me 0.008. If I work out this value as per the normal distribution table, it turns out to be 0.5032. Therefore, 1 minus 0.5032 works out to 0.4968. Using put call parity, obtain the Black-Scholes equation for the put option. Very interesting, very simple. From the put call parity, what do we have? C plus k e to the power minus r t is equal to p plus s naught, or p is equal to c plus k e to the power minus r t minus s naught. Substituting the value of c as per the Black-Scholes equation, we get S0 phi d1 minus k e to the power minus r t phi d2 minus this k e to the plus this k e to the power minus r t minus this s naught. Combining this s naught with this s naught gives me this. Combining this k e to the power r t with k e to the power r t here gives me this expression. Using again that expression, 1 minus n of x is equal to, or 1 minus phi of x rather, is equal to phi of minus x. Using this expression here, we get this is equal to minus phi d1 plus k e to the power r t phi minus t2 minus s naught phi minus t1 plus k e to the power minus r phi minus t2. This expression is nothing but phi of minus t1, so it's minus s naught phi d1, and this expression is nothing but phi of minus t2, which comes here. What is the price of a European put option on a non-dividend paying stock when the stock price is 16? This is s naught, strike price is 70, this is k, risk free rate r is 5%, volatility sigma is 35%, and maturity is 6 months, that is 0.5 years. Again we find S naught is 69 k, 70, r is 0.05, sigma 0.35, t is 0.5. So, d1 is equal to log of S naught upon k plus r plus 1 by 2 sigma square into t, that all these values are plugged in upon sigma root t, and I get 0.1666. Similarly, d2 is equal to d1 minus sigma root t, which turns out to be minus 0.0809. The price of a European put is p is equal to minus s naught phi minus d1 plus k e to the power r t phi of minus d2. Simplify this expression, you get 6.40 as the price of the put option. Black-Scholes solution. Now, before I introduce the Black-Scholes solution, see it's quite an extensive exercise, and basically the fundamental thing is that we transform the actually the problem, why it is so difficult to solve this Black-Scholes solution, why so intricate nuances are involved, is because of the boundary conditions. In the case of standard boundary conditions, it is a relatively simple equation, but the boundary conditions imposed by the call option or any other derivative, particularly the call option and the put option, make the solution beset with numerous intricacies. Now, the first few steps are very straightforward and more or less mirror the steps that we followed earlier in the context of Fokker-Planck equation. The Black-Scholes equation, initially we transform by a transformation of variables to the diffusion equation. That is the first step. We simplify this equation by making transformations of both the independent and the dependent variables and arrive at the diffusion equation. Then we use the Green function. Of course, there are different approaches, but this is one of the most common. We use the Green function to identify the kernel of the Black-Scholes equation and write the equation for the kernel of the Black-Scholes equation using the Green function approach. This leads us to the probability distribution. The kernel actually turns out to be the conditional probability of the stock price, and therefore we can write the equation of evolution of the option using a delta function, and then we impose the various boundary conditions, and finally we end up with the solution which is given by the Black-Scholes approach. So, let us start with this. I will sketch it out rather than because of paucity of time, it will not be possible to explain each and every step in detail, but nevertheless we will talk about it. The Black-Scholes equation is given here. The boundary conditions are at t equal to capital T, that is on maturity, this is the payoff for the call. We will solve it for the call option. So, C S t is equal to maximum S t minus k 0, and if stock price is 0, the call price is 0. If stock price goes to infinity, then the call price more or less mimics the stock price, and therefore it goes to S. The first step is, let us make the first substitution. We write C is equal to k into f x tau. This makes the dependent variable C dimensionless, because C and k are in the same dimension. Therefore, f, which will be our next dependent variable, which will be carrying forward, now becomes a dimensionless variable. We transform x in terms of S, the stock price, in terms of log of x. We know the log of x is normally distributed, so it is easier to handle. So, we transform the variable S into log of x by making the normalization x, introducing a variable x as log of S upon k. This also eliminates the dependence of the diffusion term and the drift terms on the on S. If by using this particular variable. Another important thing is, we make this substitution t equal to capital T. Capital T is the maturity, remember, minus tau upon this. By this transformation, because of this minus sign, we are able to transform the terminal condition to an initial condition, and this becomes an initial value problem. So, by making these are three very important transformations, and by making these transformations and writing k equal to 2 r upon sigma square, we get this equation with the boundary conditions which are given below. We continue from here in the next class. We will solve the Black-Scholes equation in a skeletal form, and then we will move on to option Greeks. Thank you.